Thank you. I'm very glad to be here. Second time. The first time is in QCMC 80 years ago. Okay. So I changed my title a little bit because I think because it's first time for me to talk about here, and I think it's a good opportunity to introduce what I'm doing and also to find some potential collaboration. So I try to give an introductory talk that contain many kind of research, and it probably will not go to very detailed, but if you have a question, you can just stop me and ask. So the title will be the quantum communication and metrology. Metrology is something we are recently doing. And of course, we know the basic principle of the superposition and the measurement induced randomness. Randomness is missed. But anyway, we know the quantum state it's described by a ray in Hilbert space, and then the superposition rules and the measurement may induce the random state collapse. You will use that one to do a quantum random number generator. Here, I just pick up one product from Quantum CTech. It's a company, a spin-off company by our university, actually by our group. And it sells the quantum random number generator just like IDQ did. So you can actually purchase such kind of thing. And it's uniform and unpredictable in principle. So I will start from the basic, because of the basic principle, we can do the quantum randomness and the device-independent quantum random number generator. We can do the quantum key distribution, frequency conversion at the quantum repeater, and the metrology and imaging. Final is the outlook of my research. Well, first of all, if I give you a black box like some quantum random number generator from IDQ or from Quantum CTech, I tell you it's quantum. Probably you don't trust it. You can see it can be a quantum state, and then the random collapse into 0 or 1, and you get it, and you know it's quantum. Oh, it's just programmable. You use some pseudo random number generator, and you have a laser either emit the horizontal polarization or vertical polarization, and it's programmed. So sometimes each time, so if you write down it's the quantum state, it's the mixed state. Sometimes it's 0, sometimes 1 is all programmed. So how could you tell it's a real quantum one, or it's just like programmed? The thing is not random here. So in theory, the unpredicted. If I give you a random number, I tell you it's from my quantum random number generator. But I actually just with the random number, you couldn't tell it's from a real random number, a QRNG, or it's just programmable things. And so you can just say, okay, it's a uniform, it can pass the test of this, but you couldn't tell it's a real quantum. So this is actually I think most of the people read this paper by Albert Einstein. He mentioned that he doesn't believe in the old one doesn't play the dice with the universe. It's just like, if you think about it in the random number ways, it's like, for people believing in quantum mechanics, you think it's measurement induced randomness, but there is also have some kind of ground theory called the local hidden variable theory. It can decide each time the measurement result is 0 or 1, but you just don't know. So how could you tell the difference? And Albert Einstein think about some quantum entanglement. Means like if two state, if it's superposition, and he think there must be some weird dynamics, so he called a spooky action at a distance. And so he want to say, okay, so if there is such kind of state, it must obey. It must have some problem with it must have some problem. So he think the quantum mechanic description of physical reality is not complete or incomplete. But later on we know the story. He has a kind of discussion with Niels Bohr. And we have the Bell test. Means like if Bell find that if you can make the entanglement source, and if it obeys the quantum mechanics, and you do that some coincidence measurement, you will violate the inequality. And if it's just if there is no quantum randomness, you just if any kind of measurement is set by some hidden local hidden variable theory, it must be less than 2. So just do the experiment. later on, I think the first experiment actually to find the entanglement is by Chen Shengwu, the Chinese lady. But later on, there are many kind of very famous experiments, and we'll see the Clausius experiment, other aspect, and Zelinger. But this three experiments bring the Nobel Prize to them in 2022. But later on, there are many, because even for this first, after the pioneering experiment, there are still some loopholes. For example, the detection loophole or the locality loophole, and there will be, so you close the detection loophole and close the detection loophole and also close the locality loophole. People think it's about loophole free, but it's actually not very free because there is still some freedom of choice loophole or the collapse locality loophole, whatever. For some people don't believe in quantum mechanics, you can probably still find some loophole. So, but whatever, these three experiments, people think, okay, we almost done here. We close the detection loophole means like all the, for the entanglement you generate, you detect about 80% of the entanglement photon pairs you have. So you probably, you demonstrate and with a very high probability, with a high fidelity, and also the measurement didn't influence each other to think, okay, in that sense, if you violate the Bayesian equality, then the quantum randomness does exist. That's the basic theory. And here we also did experiment because even with this kind of even with this three kind of loophole-free experiment, they are still using they are still need to choose the basis, because if you want to do the Bayes state measurement, you want to choose your basis. Then how could you choose your basis? They are using the random number generator to choose basis. But the random number generator they are using is a quantum random number generator. This means like you believe in quantum mechanics, and then you use the random number, and then you use that random number to test the Bayesian equality. So in that sense, there is some kind of there is some loophole. This loophole is called the freedom of choice. There are several ways. One way I think I have discussed with Valerio is just like you put people in some space station, use people's free will to do the randomness, to do the measurement. But of course, you didn't believe in the free will. Anyway, I don't know. I don't know either. And the other one is people thinking maybe we can use in some star, because this is the experiment we did in our lab. Just for fun, it's okay. The experiment is been done in 2018. We use some telescope. This telescope is receiving some sky, and this one is also receiving another star from the sky. When you know the star will the star has some emission and received by the telescope, and we detect according for example for 1 second it will arrive, because the star when the starlight goes to the ground, this is very tiny. It's a single photon. And if it collapses in the first time slot, you take it 0. And if it is in the second time slot, you take it 1. So you can using the star emission as a kind of a random number. And then this one is also get another star. And this two stars is about 11 light years away. So means like we use that randomness to do the basis choice. And then here we generate the entanglement and with very high efficiency collected with high fidelity. So means like if you didn't believe in the quantum randomness, then we use the star to do the random choice. So if this star has some conspiracy, means like this star they want to make this Bayesian equality doesn't work. These two stars need to make a deal before 11 years. So means like if we can have a big telescope, can get some 10 billion years away, then it can, because 10 billion years, there is still some light. If you can use some 10 billion years away star, and then you can make sure, okay, if they want to violate the Bayesian equality, they should kind of has a conspiracy before 10 billion years. So in that sense, we believe, okay, this one may work. That's the whole story. But this is fun. It's published in 2018 PIL paper. If you're interested, you can look at it. But anyway, so if we believe in the quantum randomness, then what can we do with that one? Just go back to the story. This is yeah, you know Arthur Ecker, he found this center. And if we have entanglement source, if we measure the Z basis, we generate a random number, right? You measure if this Alice is 0, Bob is 0, then you get a randomly, if it's the entanglement source, if you measure Z basis, you generate a random number, either 0 or 1. And the other basis, you can test the Bell inequality. And if you can loophole free test the Bell inequality, which means like the loophole can be used by the God to fake the Bell test. The loophole free Bell test means that no loophole can be built even by the God. God here means unlimited power allowed by the physical principle. So Bell test can be used to generate QRNG. The loophole free Bell test can be used to generate the loophole free QRNG. So we call this one is like device independent QRNG. And this original idea is first provided by the Mayers and Yao. Later on, there is a lot of kind of theory. And Valerio is also have a self-testing idea related to this one, but probably you ask more, right? You require the more for the device independent QRNG. But anyway, so that's the loophole-free Bell test can be used. It can generate a quantum random number generator. And okay, so this one kind of answer my question. If I give you a black box, you couldn't tell it's a quantum one or the classical one. But if this system, if the black box, if you can loophole free tell the Bell test, and it violate the Bell test, and then what you can make sure is okay, the system is quantum, and this random number is quantum random number generator. So that's the basic story. And here is the very earlier device independent QRNG. This one is by NIST Maryland using the tripline, and this is closed detection loophole. And later on, NIST and Boulder, Seunam and Crystal Cell, they using the entanglement source, and then to do they close the both loophole, and then this paper, but the entanglement efficiency is not good enough. So it's secure against the classical adversary. Classical adversary means like if the adversary doesn't have a quantum computer, it couldn't get any information from your random number. And later on, here is what we are doing. Here is our building in Shanghai, and we generate entanglement source here, and one is a fiber to go here, one fiber to go here, and this two place is about 200 meters away. And here we use the SegNet, and here is the entanglement source in the S. Basically, we are using some 1550 laser and SHG to generate 780, generate some 780 pump light. I go through the SegNet interferometer generating entanglement source. One is goes through to Alice, the other one is goes through the ball, and both detect here, both here we're using some quantum random number generator to generate the random setting and then to detect by the SNSPD with a very high efficiency. So you can see the efficiency source is about 90%. Means like when Alice detect the photon, with a 90% probability Bob will detect the photon. So this is a kind of the highest efficiency you can have for the current for the photonic setup you can have. And the whole transmission efficiency is more than 99%. The measurement efficiency is more than 95%. Means like a free space to fiber, free space, fiber. And the detection efficiency here, we use the SNSPD can more than 92%. And the physical separation is 90 meters from Alice to source, 90 meters from source to ball. And here are some, the fidelity can go to some 99% the fidelity of the state. And because you measure it, and you make sure you use very fast electronics so that the measurement, the two measurements are space-like separated, so that it will not influence each other. So in that sense, you close the locality loophole. And we close both loopholes and generate a rate about 180 BPS for the first experiment in 2018. It's secure against the quantum adversary. But later on, we increase the kind of fidelity. Now it's about 1 second. You can get about 100. You can get about 1 kbit per second. Some device independent random number. And what did we do? We actually, sorry, it's in Chinese. I'm sure it has the English version. Maybe I should change it to English version. But anyway, we put it on the website. So you can actually download and use it. And then we actually collaborate with some PQC people. The paper is published in Peanuts, no matter what. So it sounds like a beacon. So we per minute, we will announce about 512 bits per minute. And you can download a random number and for what kind of application. And here we show application is like who users, they want to do they want to do a zero knowledge proof game. Means like they don't want to they want to verify something, but they don't want each other to know the information of you have, but we want to compare something. And with this random number beacon, we can do that. And of course, you also need some. If you download, you need to make it security. You can try. You can either use in the RSA or PQC, the post-quantum kind of cryptography. You can download this authentication. Of course, you can also use in some quantum key distribution to do that, but it's a different kind of solution. And this kind of beacon, I think, is very interesting. I'm actually when we did the experiment, the first experiment in 2018, China and the US still have very good relationship. Okay, relationship. So I talked with them, like, why not we have a beacon, you have a beacon. And we co-authorize a paper like any people, for example, some people from Singapore. He doesn't believe, he just download some beacon from United States, download some beacon, random number from China, and you just do XOR. So no matter what, as long as one is really random, the number is random. So you can do a lot of such kind of thing. And of course, we can have some beacon in Singapore or in whatever the world, and then we do together. But later on, Seoul told me he couldn't, because of the policy. But anyway, so anyway, this is the we are still. If you are interested, we actually doing some standardization things. That's why I'm here for the EPSI conference, and we want to make this one as a standard kind of because this is the most secure random number. And if you make it a beacon, you can do a lot of things. For example, I don't know, some people for example lottery or some kind of thing, you really need some certified random. This is the certified randomness. Or what I have to see is the physics principle certified randomness. That's the thing. So we are still working on that. And if you are interested, we will build a kind of international kind of random beacon website. And you are interested, you are welcome to join. It seems that there is already some beacon, and this one is a quantum beacon. And second one is a quantum key distribution. So here you can generate a random, it will generate a random number. But think about Alice in US and Bob is in China. Then if you distribute the entanglement from some satellite, for example, missions, you can do the entanglement. You distribute the entanglement, and if you distribute the randomness, and then this randomness can use the K, and this is called the quantum K distribution. And you test the Bayesian quality to verify its security. So this is the basic idea of QKD. And of course, before the attacker, there is the Charles Bennett and Gil Brassa. They are thinking using some single photon and BB84 protocol. I think you know why. Later on, Bennett, Brassa, and Mermin, they demonstrated in 1992 that this one is actually similar to this one. And then, yeah, this kind of very interesting, very simple protocol bring the Wolf Prize and Breakthrough Prize for these two guys. And since I have limited time, I will just skip the decoy state things. I just start from the first project I'm doing when I came back to China, the measurement device independent QKD. It's actually, oh yeah, Rahul is here, and from Vadim's attacking on the detection. So there's think about, because in theory QKD is secure against the adversary, but the problem is if your source is not, for example, is not perfect or detection is not perfect, there will be some attack. So for example, there is a very famous attack by Vadim Makarov, is a blinding attack. Means like if we do the BB84, Alice will attend her laser into some single photon level and send it to Bob. And here for some eavesdropper, he will just block to do some measurement. And according to his measurement result, he will using some strong pulse to manipulate the Bob's single photon detector, to make Bob's single photon detector work in his way. So in that sense, he can attack this detection. So it's there are many kind of attacking method. And the solution is proposed by Huiquang Lou in 2012. Means like you have Alice and Bob, you didn't receiving any quantum signal. You're just sending some quantum signal in the measurement station, and here you just do Bell state measurement. It's just kind of like the reverse Bell state measurement. As long as you have very high efficiency, very good visibility, and you can tell it's secure against the INA. I mean, even the eavesdropper control the station, the eavesdropper can only know the kind of correlation between the two between the two quantum signal, but he couldn't tell what's the exact state from Alice or from Bob. But Alice and Bob, because they know if their state are projected into Bell state, they know exactly the other's quantum state, so they can establish the quantum K. But the eavesdropper couldn't get anything. So in that sense, this kind of protocol is immune to any attack on detector. So it's sought by the kind of secure solution for the measurement device independent QKD. And if you really want to do the experiment, for example, in the field, it's like you need two laser to make it to a single photon level, and then to make it interfere during in the real field, and then to make the two photon indistinguishable. And here is the main challenge, is to interference of two independent lasers, because you want to make the photon indistinguishable. You make sure first the spatial mode. Good, we have single mode fiber, and the polarization mode, because the fiber changes the polarization. You can use it in the polarization kind of feedback. And the spectrum and timing is a kind of ratio, because if you have a broad spectrum, it's easy to do the spectrum overlap. But in the sense, the timing, if the spectrum is very broad, the pulse is hard to synchronize, because the timing is because the pulse is very fast. But the other way, if the pulse is very broadened, then it's hard to kind of align your spectrum. And the solution is, the good thing is like for the commercial on-the-shelf kind of product, you can have some, for example, 2 nanosecond pulse width. And then because the current kind of system jitter, you can the whole system electricity jitter can control in the 10 picosecond. And for the several nanosecond pulse width, the spectrum with FWHM is 10 picometer, and you can using some commercial optical spectrum analyzer to still you can tell the difference about the two spectrum. So in the sense, if you choose this kind of pulse, you can still do the experiment. That's what we did in 2013. It's a proof of principle demonstration in China in the lab. And later on, we put it in a 200 kilometer. The main trick is we change the detector. First one here, we are using some up-conversion detector, just like ESA did. And here we are using some, we change it into some superconducting single photon detector, and then it can go to 200 kilometers. And later in 2016, we put it in Hefei, in the city. The Alice, Bob, and David. In the center is Charlie. And each one of us, we will send some, if Alice and Bob want to do the QKD, they send some requests, and Charlie using some optical switch. And Alice and Bob can do the Bell state measurement, and then Alice and Bob will establish the quantum K. And the same thing for the David. So in a sense, you get a star type of topology to do the QKD. And later on, we put it into 400 kilometers in the fiber. Just try to push, see how far we can go. But later on, people will say, okay, so for this kind of QKD, MDI QKD or decoy state QKD, whatever, this kind, because the fiber attenuated the photons. So, and for classical communication, you use the optical amplifier. But for quantum signal, you couldn't amplify that. You will bring additional noise. So the solution is if you want to really build about, I mean, there shouldn't be a problem for Singapore, but there is a problem for China. If you go to 1,000 kilometers, you probably move with a lot of kind of trustable nodes, and then to convert the electricity signal to optical to electrical, and then to do the relay. But this kind of thing, people worried a lot about the security. Then can we extend the distance? And one of the solutions is using the twin field QKD. It's a very interesting idea. Means like you can think about this is the general the QKD, the sender to the receiver. If it's 100 kilometers, the loss is about 20 dB. And for the MDI QKD, also for the sender go to 50, this one go to 50, you still get about 20 dB loss. But if the two laser is locked, if the laser frequency is locked, and the two laser interference, when there is one and only one photon click, means like it's like a half Mach Zehnder interferometer. Means like you have a laser, you send it to Alice and send to Bob, and if it is laser locked, and then they do interference. But if the phase are locked and the laser frequency are locked, then we will know, okay, there will be, if there is one and only one click, means like the phase is the phase difference 0. Or if it's here, means like the phase difference is pi. So in that sense, you can lock the two laser frequency, and you can do you lock the phase of the whole fiber, then you get one and only one click, there will be a kind of half Mach Zehnder interferometer. But in that sense, because the photon is actually just like go halfway, because in MDI QKD there is one photon, but in TF QKD there is only one photon click. So it means like the total loss is only half. In that sense, if for example, for the BBA4, the efficiency is about eta, for example, 100 kilometers is about 20 dB. But if you do the QKD for 100 kilometers, only 10 dB loss. So in that sense, you can extend the difference. So that's the basic idea. So in the sense that since MDI QKD can go to 500 kilometers, then this one probably can go to 1,000 kilometers. That's what we did in our lab. And because here for the Alice and Bob, they didn't receive any quantum signal. They still sending the light into some measurement station. So this means this one is still MDI security, means like a measurement device independent security. But this one is kind of challenging because you need to control your laser frequency, because you know if you are in the lab, you know actually your laser jumps very randomly, and you should lock your laser frequency, and also you should control your fiber, because we know the fiber if it's in the field. I mean, any kind, for example, the temperature changes or the even some noise. For example, if you walk around your fiber, it may change the length of your fiber, and it will change the phase. So it means like if you want to do such an experiment, you should lock in the frequency of the two remote laser. Instability is about per second 20 minutes 14. I mean, it's good thing is this one is already been done for the people who is doing the optical clock. If they want to compare to optical clock, they want to lock the two lasers remotely. And this, if you notice, this is the paper by the PTB people. It's already been done in 2012. It's a field test. We just adopt this technology into our experiment. And the only thing is the fiber length fluctuation. Here is the kind of solution. First of all, we have a laser, and all these two lasers are locked into the ultra stable cavity. And this cavity is the cavity is very stable, and then the kind of bandwidth for this laser is less than 1 Hertz. So it means the coherence time is more than 1 second, something like that. And then the laser will go through the fiber. For example, this one is a 500 kilometers experiment, and we use some bidirectional EDFA. Means like this laser signal will go through the fiber, and the other laser will go through this. One laser go this way, the other laser go that way, and the two lasers will interfere here. There is they will see the two lasers kind of you look size the interference of these two lasers, and this laser signal, this kind of interference signal will do there will be interference. Here is the interference, and the interference difference between this two signal will go through to this to be feedback to the AOM, and the AOM will change the frequency to make the two lasers frequency lock together. This is a kind of standard technology actually developed by the Junior group in NIST and PTB. We just adopt this technology in our group. So it's like when this has been done, these two lasers are locked, and then we use some very tiny part of this laser to do the quantum things. And to do the quantum things is like, then the next step of the work is how could you make sure, if the laser is locked, how could you make sure the fiber fluctuation won't change won't influence your experiment? What we done is about, for example, we have some quantum signal. We use some time multiplexing, we put some classical signal together. Sometimes it's quantum, and then later in the time slot, first the quantum signal and the classical signal. And then we measure the classical signal. We know when it happens, the phase changes of the fiber, and then you can do the feedback, and then you can kind of fix the fiber fluctuation with this experiment. And we achieved 500 kilometers in this paper in 2020. And later on, we were thinking, how could you do the real field test? Here is what we done in Jinan and Qingdao. This is our lab, and we rent a room here. We send the laser here, and the quantum signal here. Just in the middle, we call it Mazhan. We actually rent cables. This is 12. This cable contains 12 fibers, and from 1 to 8 is for classical communication. It transmits a lot of information. And then we have 9, 10, 11, and 12. And for the number 11 fiber, we do the QKD. And number 10, we are doing the synchronization. And we also the wavelength calibration. Wavelength calibration, what I mean is to lock the two lasers using the number 9 and number 10 to do the synchronize. But of course, number 9, number 2 can be a fiber. But because we have many kind of axes, so we just doing this experiment in the lab. And there is actually a lot of noise from the other channels. And you can see there is kind of noise. You can feel, you just choose we choose our wavelengths in some 1530 something. And here is the main noise from the classical communication. There will be crosstalk to your quantum link, and the users filter it out. And here is the phase fluctuation you can see, and you can do the feedback. And here is some polarization fluctuation, and you can use the feedback to make it is a very good efficiency. And here you can see it's different. It's the temperature changes, and the red spot is the temperature changes fluctuation, and the green one is the fluctuation, time fluctuation of your photon pulse. And if you can, and we are using our method just to fix the fiber fluctuation, and you can see here the yellow line is after feedback. You can see all the kind of phases controlled. And we get about 500 in the real field. And later on, we decided we go to try to see how the system to point QKD, how far we can go. And that's what we did in the Jinan lab. We actually using several methods to reduce the noise by the class signal. We may introduce some noise photon. It's a really scattering, and we use the dual band phase estimation, and the Raman scattering, we use the time multiplex reference light. And for the dark count, we use some ultra low noise SNSPD developed by our collaborator. This one is about 0.1 count per second. Means like about 10 seconds, there will be a dark count. And eventually we get about 1,000 kilometers. Means like with 1,000 kilometer ultra low loss fiber, you can still do QKD. But the K rate is very low. For this one, I think about the 300 or 400 is a reasonable kind of reasonable distance. So in the future, I think maybe per 200 or 300 kilometer, we will put a classical node, because in China there will be a major data center for the major city about 200 or 300 kilometers. So we can just put your trust node in the data center, so you can guarantee the security. So it can be more practical, and the K rate is still 10K BPS, 20K BPS, and you can using that one to do the QKD. That's the basic idea of what we are saying. And good thing is for this kind of interference, it's very kind of it's very alert to the vibration, and to if you're walking around, you bring a lot of noise, but this noise we can feed it back. But when you are doing some feedback, you actually get a lot of redundant information, and you can using this redundant information to do the vibration sensing. We published this paper, and we are now trying to build up because this one is still in the lab. So we are thinking to build up in the field, because in China we have many kind of we have a kind of earthquake place, the belt between so we can using this kind of we are thinking to, because in China we have about around 20,000 kilometers kind of QKD network. We want to first try to replace the QKD network with the twin field QKD to do the interference. So in that sense, maybe in the next 5 years, something, we will build up some network all over the country. So in the sense, you can do QKD, and also you can measure the kind of vibration of earthquake or whatever, and see what we can do. It's just like we build an interferometer over the country, something like that. And I'll go to the third topic of quantum frequency conversion of quantum repeater. And here, this picture is good to see that if you see the decoy state or MDI QKD, and this is the distance, or you can see the fiber loss, and here is the rate. You can see the decoy state MDI QKD, it will decrease very quickly. And if you use TF QKD, you can increase the distance. Means like you can go to even 1,000 kilometers. But the reasonable K rate is still about 300, 400. But how about 1,000 kilometers? Can we still go to some 1,000 qubit per second? You use a quantum repeater. Means like a TF QKD is like the one-step quantum repeater. But if you have many quantum memories, you can do the multi-step TF QKD. It's like you can do the quantum repeater. So that's probably the way to, if you are using the fiber, you can go to the very, very, very long way. So, but for the basic idea of quantum repeater is like you have many nodes, and between each node, you build up the quantum entanglement, and between each node, you can do the entanglement swapping, and then you do a lot of entanglement swapping. Eventually, node A and node E will be entangled, and you use this entanglement to do QKD or whatever you want to do. But the thing is, like, you need to have entanglement swapping. You need you need first to generate the entanglement between node A and node B with very high efficiency, with very good fidelity, and then you need entanglement swapping. And also for each side, you need, because the quality will reduce when you are doing the entanglement distribution, so you need the entanglement purification. So for such three kind of thing, with such a kind of technology, you can do the quantum repeater. That's probably the main task for the next step of quantum communication field. So here, I'm not doing the atomic. I'm not atomic people. So this is slides from my collaborator Xiao Guibao. It's his result. He's just using some rubidium code atom ensemble, and with very internal retrieval efficiency with 88%, and the fidelity about 93%. What I'm doing for him is like, because his wavelength is about 795 nanometer, and this is not good for fiber transmission. If you really want to do the field things, you need to do the kind of frequency conversion, convert it into some telecom band. That's also is a bit. And you need to convert this 795 nanometers light into some 1310 or 1550. 1550 is good because it has a low loss in the fiber, 0.2 dB per kilometer. So that's we fabricated the pipeline PPR1 waveguide. With the first experiment is using the signal is 795 from code atom ensemble, and here is a 1950 nanometer pump from thulium doped fiber laser, and we use the directional coupler. We fabricate on the pipeline waveguide, and then to do the positive phase matching here, and to do the frequency conversion. This is mainly done by Miyang sitting right. And here is what we get. We get about the internal efficiency about 70%. The overall efficiency from the 795 input and the output about the 1310 is about 33 point, and the noise about 2.5 kilohertz, and there is some nonlinearity. The 1950 we go to some Raman scattering. There will be some undisclosed noise photons, and then the signal noise ratio is more than 20%. So in the sense you can do the quantum stuff. And the basic idea is you are using the quasi-phase matching issues. You have the waveguide. You use the quasi-phase matching to match this the k vector, and then you get and this is a quantum frequency conversion because you still keep the quantum state there. You still keep the quantum statistics. Here is how good we fabricate. We have about 400 square meter kind of clean room to do we have the lithium niobate wafer, and then to using some lithography, and then to do some high voltage because and we use some high voltage to make the periodically polling regime, and then we use some we put some silicon dioxide on site, and then using the lithography to define the waveguide pattern, and then using some proton exchange and the APE waveguide, and eventually you do the reverse exchange. This idea is actually, this technology is learned from Matthew group in Stanford University, and we built up our own setup in China. And now we are doing not only the RPE waveguide, but also the kind of the rich waveguide, and also now doing some thin film like they did here. And here is what we have. We actually already make this one as a product. We are selling inside of China. And you can see our propagation loss is about 0.1 to 0.117 dB, and the conversion efficiency is 99.9%. The fiber peak timing loss is less than 0.5 dB. And we collaborate with Xiaohui. We did about 50 kilometers coiled fiber and 20 kilometer the field deployed fiber with the code atom ensemble to do. It's a 2020 experiment, just using our frequency converter. Very recently, we put in the Hefei city. We have Alice, Bob, and Charlie with a server. There's 3 code atom ensembles, and we can build the entanglement between each node. And this paper will be you will see it soon in Nature. And what we are doing is we just provide enough kind of frequency converter for them. That's the basic thing here. So I can see this is probably the first metropolitan kind of with quantum memory quantum repeater. But we are thinking to extend this distance to about 300 or 400. But of course, for code atom ensemble, the problem is it's very hard to do purification. So we probably need to change our system to do some Rydberg system or other system. That's the basic thing here. And we also work with my colleague Chaoyang Lu. He has a very fancy quantum dot. We convert his quantum dot into some 1550 and then do the interference about 300 kilometers. And the paper is published in some advanced photonics. Okay, let's go to the metrology. We all know that in 2018, we decided that the international system units, the ISI, will be based on the quantum. It's like for all the kind of the ISI units, we're using some quantum number. We're using some constant number of quantum physics or just the physics constant to redefine the fundamental constants. And actually, except for the more, all other kind of like the ampere or meters or kilogram Canberra and temperature are all related to the second. So it means like the second definition is probably the most important thing. And the second definition is actually the most precise measurement of the whole kind of unit. And currently, we are using the cesium's microwave kind of transition to define the second. But recently, people find if you use optical clock, you can actually get about 2 orders better even 3 orders better than the cesium clock, than the current one. So then people will think, okay, can we using the optical clock to replace the microwave clocks? But there are many, also there will be, but if you want to do the kind of redefinition with the optical clock, then what you should do is you should have many institutes have very good optical clock. Now NIST have good clock, PTB has good clocks, and here has good clocks, and China we have clocks. And you also need to compare all these clocks. Means like you need to do the average of all these clocks. And for the cesium, it's easy. You can just using the microwave. You can use TPS to do the because this one the transition is microwave. You're just using the microwave to compare all this clock. For the optical clock, it's in the optical regime. So you should find a way to do the comparison of to connect all this clock. And if you can connect all this optical clock, you can actually did a lot of things, except for the redefinition of the second. You actually can do the you actually can do the fundamental physics test, for example, the general relativity, the gravitation test, the dark matter search, and precise navigation. But the problem is, you do the optical clock comparison between, for example, intercontinental between China and US or Europe. So the solution is like. I just mentioned in the fiber side, the PTB already did this one in 2012. They can do the fiber base. So inside of if in the kind of in the continent, you basically you can use fiber to do the same. But how about intercontinent? For the cesium clock, we use TPS. But for the free space, for the optical regime, you couldn't using that one. So that would be a problem. So that's what we are working on. And this is in the Xinjiang province. Here we use frequency comb. Frequency comb will we have a frequency comb in 1 watt frequency comb with the stability, with a very good stability, and with a very good coherent detection here. And in the Xinjiang province of China, we have about we choose about 100 kilometers of ways optical links. It's a free space one from Nanshan to Gaoyazi, another place, and with the telescope with about 400 millimeter telescope, and we send it out frequency comb from here to Nanshan to Gaoyazi, and the Gaoyazi is also back, and just like a fiber did. But here is in free space. For fiber, you're just using the CW laser with locked into the ultra thin cavity, ultra stable cavity. But in the free space, you couldn't use the CW laser because there will be some turbulence. If it blocks your light, and then you actually couldn't find the interference pattern. So in the sense, you need using some pulse laser, but pulse laser actually is not very stable, except for the frequency comb. The frequency comb is a kind of a pulsed CW laser. It has a very strategic kind of line. So we use the frequency comb to send to each other, and we get the time frequency determination means about 10,000 seconds. We can go to a 4 times 10 to minus 19. Which means like we can compare the clocks because the best clock is also around this level. So if you can do in the ground station, you can do 100 kilometers, which means you can do the satellite ground measurement between we will put us in 2 years later. We will put about optical clock on the ground state. We will launch another new satellite. It will go to the GEO, eventually it will go to the GEO orbit, and it will have a optical clock. It will compare the optical clock with the ground station optical clock. And this experiment demonstrated the feasibility because the loss for the 100 kilometers is much larger than the ground station to the GEOs, even larger than the GEO satellite. So it means like this one tells like our system can work in that purpose. Means like we can compare the optical clock with China satellite to the ground station, and that one to the US or to PDB, or if here is a clock. I went to the ground station here, and then our ground station for this purpose will have a 1 meter telescope. your telescope is a little bit smaller. It's about 300 millimeter. So you probably need a higher power laser than to go there. But I think it's still possible. So in the sense, I think if you have a good optical clock, we can do the clock comparison between China and Singapore. And of course, because we are doing the experiment in the free space, means like you actually have a lot of carbon dioxide and the water absorption for this the whole kind of 100 kilometers. So in the sense, you can measure the spectrum of the carbon dioxide and the water. This kind of method is called the dual column spectroscopy. Before we can only go to 1 kilometers, and our experiment shows that you can do 100 kilometers spectroscopy. And this one is you can use it for some application. For example, if there is a satellite between the ground station and there is a satellite and the ground station, then you can measure the whole kind of carbon dioxide emission from the column from the satellite to the ground. And then you can know you can tell the status of the global carbon dioxide emission with the satellite. That's also one thing I'm thinking. And this one, because you are doing the time frequency dissemination, you can actually measure the distance very precisely. And for this one, we demonstrate that for our experiment, we can demonstrate the distance change into some nanometer. The best one is about 82 nanometer per 20 seconds. Of course, here we eliminate the turbulence. We can calculate the turbulence. But if think about it, there are two satellites in space, there is no atmosphere. Then you can use in this method, can measure the distance between to go to some 20 or 80 nanometers. And then it's very important for many applications for the satellite to synchronize the satellite. You see is what we are doing here. And here is, I think this the HBT, people ask me about that because I don't know whether you know this paper published in a very early time in 1956 by the Brown and Twist. Means like they are actually using 2 microwave detection, and then before people want to observe some, for example, if you want to check some star, we are using the interference, means like a Mach-Zehnder interferometer or Macrauchon interferometer to observe the star. But these two guys, they shows that even to because before it's just like it's like a star has some light to go to they use a Mach-Zehnder interferometer, means like they use a one-fold interference. But here they show that even you use intensity correlation, you can still doing some measurement. This is the basic idea of this one. They show that with this kind of HBT interferometer, you can measure the diameter of your star. Kind of people actually using this one to using the intensity measurement to measure the diameter of the star. And the good thing for this one is you need to care, you don't need to care about the phase changes because of turbulence, because this is just an intensity measurement. So this is the paper. And later on, then the problem is but here there is a requirement. It's like you need the star has the same wavelength. If the wavelength is different, you couldn't observe the interference. Means like if there is, for example, this is a star, and here is the star is like this size, and the one side of the star has some red light, and the other one has some green light, some blue light, and you will see that you couldn't observe this HBT interference with for different color. So the problem is, can we do the kind of different colors, achieve the HBT interference with multicolor sources? And the solution is provided by Jordan Coulter and Frank Wilczek in actually the paper published in 2012, but they put the paper on the website. The basic idea is if your detection can do some coherent conversion, for example, your detection can change the blue color into some blue color and the red color coherent superposition, and the red color into some blue color and red colors superposition. then you can do you can measure the HBT in the parameter. But if you are familiar with the nonlinear optics, you will know this is just like the sum frequency of it's just the sum frequency generation, like what we did with the PPRN waveguide. So Mingyang and Luoyuan, they using our PPRN waveguide to observe this kind of detection. It's called color erasing detection, and we observe the HBT effect here. We can see here is in Shanghai. And here we find some 1.43 kilometers free space channel. And this is we rent a kind of apartment. And we have some two lasers, two laser pointer. They are kind of 4.2 millimeters away. And then we use this kind of HBT interferometer. We can observe improve the spatial resolution. And then we can get about 40 times higher than the diffraction limit using this method to observe the HBT interference. This is a very recent experiment. It's like we're using the parallel lasers to shine from outside of the patents, and then to using the LiDAR method, because the LiDAR generally people using the laser. But the laser, you couldn't observe the HBT effect because only the thermal light, you can observe the HBT effect because the laser is some kind of based on Poisson distribution, and there will be no HBT interference. But if you are using some laser without the phase lock, and then you can still observe that one. That's we developed that theory, and then we can observe about 10 times diffraction limit for this LiDAR. So we are thinking this way can be used to observe the space debris, because there are many space debris on low Earth orbit. Because people are still trying to launch as many as they can the low Earth orbit satellite, like Elon Musk did. But eventually there are many debris. But how could you measure the debris? Because the debris they didn't they themselves is not the light source. So you need to have some LiDAR. But the LiDAR sometimes has some diffraction limit. So if you are using some method like the HBT interferometer, then you can do the super resolution LiDAR. You can observe the space debris. That's what I was thinking. And okay, here is I'm sorry, it's in Chinese character, but whatever. We want to build that's the fiber QKD network we have in China. And we are thinking to replace this one with some of them with the twin field QKD network. In that sense, we can do the time frequency dissemination. We can compare optical clocks, and we can also measure the vibration. We can measure the earthquake. There are many kind of the gaps between the earth, the rocks, so that we can measure that. And we also have two satellites, the Mission satellite and the Jinan 1 microsatellite, and we can do of course I want to find the collaborators here. Your ground station can have the collaboration with us, and if you have good clock, we can compare. And in the future is like because I don't know, I think maybe in 5 to 10 years probably we can build all the QKD network with the twin field QKD. We can measure a lot of things, and if you can synchronize very well with the different kind of telescope, you can build up the big kind of HBT interferometer, or you can build up the Mach-Zehnder interferometer, and you can have a super resolution of the. You can check the stars. You can check some valuable atomic objects, and also maybe later we can put some quantum memory there, and then see what we can do. That's probably the long baseline HBT interferometer, or long baseline the VLTI or whatever. And here there's many collaborators. Here is our group, led by Jianwei Pan, the center. And the work I'm talking is for one group, but there are also some people who are doing the superconducting, Xiaobo, and Cheng Zhi is doing the free space things. And a lot of people doing atomic, and Qiang is doing the quantum computer. Fei Hu is doing the single photon imaging. Yao is doing the cold atoms. And then the optical clock, the molecules, a lot of researchers. And I get a single photon detector from Li Xingyu. He probably the one of the best superconductor thermal detector. Xiangbin Wang and Xu Fengma are doing theory. Haifeng is doing the frequency comb. And Frank Wilczek provided an idea for the imaging things. Thank you.